Good day, dear guests. Welcome to the next lecture. It's about OpenPCD and OpenPICC. It's a free software and hardware RFID reader and emulator. And so, please welcome the world-famous kernel hacker Harald Welte and please, and a software expert Milosch Meriac.
Hi, thanks for the welcome. I'm going to talk more about the general aspects of the project and the software aspects of the project, whereas Milosch is going to talk about the hardware aspects, and we're going to change back and forth during the next 2 hours. As for the general schedule for these 2 hours, initially we'll be doing a presentation about the architecture of the specific hardware and software in use. Afterwards, we're going to do a demo of how to use OpenPCD and how it can be used in combination with lib RFID. And in the end, I think we will have enough time for questions and suggestions, whatever. Okay, so for those, a small slide about who I am, what my background is. I'm mostly known for Linux kernel work. I've recently got more and more into embedded stuff and finally into hardware, such as the OpenPCD, OpenPICC project. I'm also working on Linux mobile phones and some other stuff. Initially, I got involved into RFID in general, mainly through the CCC, the Berlin CCC, and also mainly because the German government decided to introduce biometric passports. So basically, I had to have a look at the security aspects of these passports in order to do so. Lib RFID and the other stuff started. Okay, so I'm going to keep this very quick. There have been a number of RFID-related presentations, and I think most of the basics have been covered by now. What we are talking in this presentation about is 13.56 megahertz RFID systems. One of the fundamental characteristics of these systems is that they are magnetic coupled. Basically, the tag and the reader forming a sort of more or less open transformer between each other. The common standards and non-standards in this area are ISO 14443A and B, which are called proximity IC cards. There's ISO 15693, which are called vicinity IC cards. And there's a number of proprietary or more or less proprietary systems, such as Sony Felica, Legic, MyFair Classic. And it's mostly used for cryptographic smart cards and for identification purposes. So if you look at existing RFID reader designs, as in commercially available products, for the 13.56 megahertz RFID standards, then most of these readers you will find are based on an ASIC design from Philips, most likely. Well, now it's NXP actually. Philips Semiconductors has been renamed, also Texas Instruments, and a microcontroller next to it. If you have readers that are not standalone devices, so readers that you can attach to a PC or something, you will have a USB interface, you will have a serial port, or you have PCMCIA, compact flash, whatnot. There's also some reader designs which have Ethernet or even RS485 or similar protocols. And one of the important things driving this kind of reader design is that if you want to support the proprietary MyFair Crypto 1 algorithm, then you need a Philips or now NXP reader ASIC. There's no other way, because the whole security of that system relies on the obscurity of the encryption algorithm. And the encryption algorithm is only implementations of that algorithm are only available in hardware. One implementation is inside the transponder, and the other implementation is inside the reader ASIC. And unless you have the reader ASIC, you will not be able to support the very popular and infamous MyFair Classic standard. There's basically two categories of readers. One of them is what I call active readers. The other one are passive. The active and passive is not, it's always actively emitting a field. The active and passive terminology does not refer to the radio signal or anything like that. It's just like where does the RFID stack run, the actual protocol stack for the ISO 14443 protocol, for example. It can either run in the device firmware, so in the reader itself, the reader forming an sort of an autonomous PCD side implementation of the ISO 14443 protocol, or the protocol can run on the host PC. Most of the readers that you can get, or that I've found, are active readers, which have some or even all of the RFID stack inside the device firmware, and a number of them, a smaller number of them, most notably the OmniKey 5121 and 5321, I think. They implement the RFID protocol stack in the host PC. And that's basically something that is more interesting if you're interested in security research or anything like that, because with any of the commercially available readers, you cannot just change the firmware and change certain aspects of the protocol stack, violate timing specifications or stuff like that, or send packets longer than you are expected, and all these kinds of things you cannot do with the intelligent readers, the active readers, which have the firmware implementation of the stack. Maybe a little bit of history. 19 months ago, I started the librfid project, which is basically a GPL licensed implementation of an ISO 14443 A and B, and MyFair Classic and MyFair Ultralight and ISO 15693 implementation, which runs on those passive readers, where the RFID stack runs on the host PC, and the reader actually just acts as a dumb transceiver between the PC and the RF world. And then later on, we started the OpenPCD project. We went one step further, not only having our own free software implementation of the RFID stack, but also having our own free implementation of the RFID reader. And OpenPCD basically is a reader design that gives you full power and control of all the interfaces. The reader hardware design is under Creative Commons Share Alike attribution license. The reader firmware and host software under GPL license. The hardware does not require any proprietary development tools. This was a very key aspect during development, that anyone should be able to program or reprogram or alter the device without having to invest or, without having to buy any kind of programming adapter, without having to buy any kind of proprietary compiler, development environment, license, external operating system code or whatnot. So basically, the firmware is written from scratch. There's no, Nucleus or RTOS or whatever kind of operating system in use. The hardware does not require any programming adapter for reprogramming. You cannot brick that device. It's impossible. I mean, as in, obviously you can put it in the microwave, but you cannot brick it by flashing something that doesn't run. You can always recover, but just by using a USB cable. You don't need any programming adapter, no JTAG, no whatever. Thanks. So the idea is that we can modify the firmware. So this means we can build an active reader or a passive reader with that. We can also build something that's not a reader at all, that just transmits arbitrary patterns and sends them, whoever is interested in that. You can produce protocol violations, and that's where the interesting aspect starts. So as for the hardware, Milosch is going to demonstrate shortly what the hardware looks like. Basically, just a raw overview. We have very much like the commercially available readers, we have a microcontroller, which is a very large microcontroller in our case, and in addition to that, we have a Philips reader IC. And again, we have that specific Philips reader ASIC just for supporting the MyFair protocol. But then Milosch can take over and talk about the actual hardware design, how it looks like, and how the individual parts integrate. And after he has shown his slides on the OpenPCD hardware, I'm going to take over again and talk about the firmware design and the firmware development environment and the USB protocol and the host software part of it. I'll be back.
Hello, I'm Milosch Meriac, and as Harald already indicated, I was responsible for the developing the hardware. I'm a hard and software developer, do it basically for a living. We are a small company consisting basically of me and my wife. She's here in the front. She does the PCB designs for me, and so we are a neat company that does custom tailored embedded Linux systems, hardware platforms adapted to customer demands and stuff like that. I will introduce you in the architecture of OpenPCD, so you get a rough idea if you want to approach a problem where to start searching. So just to be sure that we are talking about the same stuff, there are some misunderstandings with RFID. Basically, RFID looks like this, that most of you already know, that you power the device by the reader field. So you have a very strong carrier. The data is modulated onto the carrier and obviously can be easily read by the power tag. But there is no active transmitting from the RFID device. The back channel from RFID tag to reader is done by load modulation. So as you see in the picture, the idea is that you have something like an open transformer. The coupling is inductive, and you can can you properly hear me? Yeah. Okay. You have basically a diode that is meant to demodulate the carrier and to remove the carrier frequency, and Zener diode to clip high voltages. And the back channel is by applying a resistor to the input RF interface. Pardon? Yeah. I just hurried here, so I'm a bit excited still. Okay. Yeah, we are talking about 13.56 megahertz. This is basically the current, mostly widespread technology. It's mainly used for transportation. And the upcoming technology is this 800 to 900 megahertz stuff, but this is mostly common. There are currently nice security features already included, so if you want to use it for secure application, then you definitely have to stick to 13.56 megahertz. To my knowledge, at UHF, there are no real security features enabled yet, so if you want to have doorway applications based on our reader, then it's a good start to use cards that provide active cryptography and stuff like that, and you get this basically only in this frequency range. So it's definitely possible to use the stuff for secure applications where money is involved, or you have sensitive area to protect. The reader to tag transmission is the AM modulated carrier. So you basically increase and decrease the power level of transmission, and this also means that this can be easily picked up, and you can, for example, use software-defined radios to watch actively transmission even from far distances. The tag to reader communication is very hard to sniff currently because the load modulation introduces a small shift in frequency basically, and you can't sniff this easily because the dynamic range between the carrier and the data is pretty high. So the best approach to learn something about these protocols is to actively emulate such devices and try to find out what's going on. Our device consists of a 32-bit ARM controller. This sounds a bit overpowered, But concerning the fact that we are not planning to sell it in high quantities, that is meant to be a device for open source projects where you have as few as possible initial costs. And to my knowledge, there is no reasonable 8-bit compiler for microcontrollers in open source world. So you want to stick basically to 32-bit compilers. The cost difference between a 32-bit CPU and an 8-bit CPU is only a few euros. So for a small volume project, it definitely doesn't matter. So the idea is that, or our intention was that with 32-bit architectures, you get far more people that can contribute because there are no special features of 8-bit world to be considered. You basically program the same language that you use on your computer. And this is what we wanted to achieve. The library and the firmware we provide to you provide really high-level functions that you already know from host computer world. We have functions like printf, where you can print messages on a debug output, so you can quickly find errors and you can develop your stuff without having to know about the very internals of the CPU. Basically, it's shielded by our API. Maybe we'll ask that why we used this proprietary RFID reader IC, this RC632. The idea was that we wanted definitely to support MyFair cards. The MyFair cards are the cards I mentioned before that are used for transportation purposes and for example, as access control cards. The disadvantage on this card is that the cryptography algorithm behind it is not documented at all. So currently there is no possibility to talk to such cards unless you use the RFID reader ICs provided by the very same manufacturer that manufactures the tags itself, in this case NXP. So basically we only use this for providing MyFair support, and I think this is inevitable if you want to have a RFID reader. The RFID reader IC natively supports ISO 14443A and B and 15693. But we wanted to provide also support for proprietary cards that are not directly supported by the reader IC itself. To make this possible, we provided an interface where you can basically bit bang arbitrary bit pattern on DMA accelerated output. So this. Okay. Huh?
I don't know what they did. They cut off all the high frequencies and you only have the low frequencies and you have all the...
I try this. Hopefully this is better. Okay. The idea we had is that most of the protocols that are involved in this technology need well-defined bit patterns that fit to the oscillator frequency of the RFID reader field. So to make this possible in this device without breaking your fingers when programming, we basically took the carrier frequency of a 13.56 megahertz reader IC and feed it back into the ARM controller and use internal timers to scale it down to a frequency we want to have, basically the baud rate or whatever. And then we put this frequency again on the output pin, which is fed back into the reader IC again, and works as a clock for the DMA interface. So this means that you can time your whatever protocols you decide to use, you can time them very exactly to the reader frequency, the 13.56 megahertz. So you don't have to do the timing in your software. You just can pre-compute the bit patterns, and you just start a DMA request, and they are constantly clocked out at the baud rate you expect. and this solves a lot of problems for you when emulating stuff. And with this approach, with this time ICs, you also have the possibility to change, for example, the pulse width, and you can, for example, change the phase of the clock signal as you want. So you can do really nice tricks with this approach. For people that want to have complete access over the device, we provide a JTAG debug interface. We didn't solder the header by default because we have to spend up to several hundred euros to get such a device to be able to debug such code at assembler level. But I think most people won't need it. The debug interface is good enough. You can do printfs, and the most hairy stuff is solved. Harald wrote a great bootloader, which is able to be refreshed instantly during runtime. It only takes a few seconds, and you get a new firmware. You don't have to press strange key combinations or buttons on the device. You can instantly flash them, and this results in a very quick programming style, because you can, for example, create a target that says make install, and it immediately uploads the changed code, and with the debug interface you have perfect overview what's going wrong. So what we want to achieve with this talk is to take the fear away from you that, oh, we better design, it's so crazy, and all the strange routines that nobody understands, and it's so abstract and whatever. But we tried to make it look as common as possible. You find all the routines you need there, and you have very high-level functions, and you can execute them without having to know what happens below. So I think for most people JTAG isn't needed. What we also wanted to achieve, we intentionally choose a relatively big microcontroller. We don't use it that much flash for the common read applications, but the basic idea is that you can store the complete RFID protocol code inside the reader. This means that you can attach, for example, the reader on a door, and you can use one of the I/O pins we provide or the serial interfaces to, for example, trigger door contacts and stuff like this. You don't need a PC to solve this. So we try to provide you reasonable interfaces. For example, with I2C, you can directly attach displays. For example, you can display the name of the person coming in or whatever. Or with you can reconfigure the I2C pins to I/O pins. This enables you, for example, to trigger relays and whatever. So all the code can run inside. It fully understands RFID cards. It can do anti-collision. It supports multiple cards in the field. You can even detect what cards are in the field. It's very convenient. And you can test your code locally in your host computer, and you can recompile, cross-compile your code and have it installed after testing on your inside your firmware. So this is how we want to achieve that you have as few as trouble possible. Another idea is that oh no, okay, let's skip this. This is how the reader looks like. We wanted to keep it as inexpensive as possible. You have this standoff spacers, so it's basically only the PCB. You just turn it upwards, and surrounding the reader there you find the embedded antenna. The trace you see running around the top and bottom layer on the picture is not the antenna itself. It's just a shield to protect, to remove the electrical component of the field, and only use the magnetic component. The real antenna traces run inside the second and third layer, and you can see how the internal structure looks like on this slide. On the red one is the top layer, and the second one is the intermediate layer, where you have 2 turns of the 4 turns. You can see them on the dark red part. You also have the possibility to adapt it to external antennas. We used 0-ohm resistors to connect this antenna. You just remove them, and you have a 3-pin 2.54 millimeter spaced header to connect another antenna and do whatever you want. So basically, you have to do your own antenna adaptation in this case. And if you want to do boosting of the signal to achieve bigger reading ranges, then you can tap into this interface too. So just to be aware what the current reader can do is, so usually the reading distance for this kind of reader without boosting is depending on, naturally depends on the card, because some cards use protocols which make it much easier to be read from a remote, from a far distance, and other cards simply take up too much power. So the reading distance is between, say, 8 centimeters down to 2 centimeters. The nice thing on this device is if you want to really learn something about protocols in there. For example, you want to see what actually happens on the RF interface when you're issuing comments. You have 2 possibilities. There are 2 interfaces called MF-in and MF-out, and these enable you to see intermediate coding and decoding stages of the this RFID front-end chip. So, for example, you send data and you can see that the unmodulated data, and you can see the encoding and can trigger to it, and you get a pretty good idea what happens on the interface. And for example, if you try to increase the range, you can see what changes what happens in the digital part if you, for example, increase the range and whatever. Also nice task if you're interested to find out about not well documented protocols is that at the same time you use, for example, this undocumented functionality, for example, by talking to MyFair ICs. These are completely handled transparently by the reader IC. Basically, there is only few knowledge about this. You can issue this comment. The comment is translated into RC632 action, but you can, in parallel, you can sniff what happens, what the reader sends to the tag actually. So this is, for example, a nice use case for this MF-in, MF-out interface. And also this is the place you want to tap in if you want to support protocols that are not supported by the chip natively. There you have the same approach. You get the oscillator frequency, 13.56 megahertz. You use the timer input to derive the clock frequency you intend. You can adjust the phase, and you configure your DMA output to sample or transmit data that you can pre-calculate. So this makes emulation of protocols that are not supported very easy. This is an example I just want to show what you can see. You see the data, then the first encoding step, and the resulting pattern on the RF interface. And this is on the RX side, you see the load modulation pattern and the resulting decoding steps. To have this easily accessible, you have to be aware that the reader provides a strong magnetical field. So if you just tap your oscilloscope probe there, you get a lot of noise by the carrier frequency, and so you get a huge amount of distortion. So we decided to use this U.FL connectors, which you know already well from wireless LAN cards. These are these very tiny HF connectors to bring out these critical signals. And we provide some cables which can be used to easily connect the 3 outputs I told you about to oscilloscope or whatever. We also provided a trigger output. So this means if you have a complex protocol, you decide by yourself when you provide a pulse on the trigger output, and you can this enables you to trigger your oscilloscope to any state of the protocol without having the need for a high-level oscilloscope which can trigger to logical symbols. So this is the idea on the trigger output. It's basically a simple I/O pin, and you decide when to send a pulse so your oscilloscope can trigger on a well-defined position in the protocol. Yeah, I already talked about this, that it can be used standalone. There is plenty of space for your own applications. And it basically, if you, for example, have existing machines which you want to extend with RFID technology, for example, access control, or you have a vending machine or whatever, or then you can isolate this complex RFID protocol stack completely from the device. You can just remove it to your, for example, use it only to read the data out of the device, authenticate to it, and to get the data you intend to use, and just, for example, send it out on the integrated RS-232 interface. So your target application doesn't have to know anything about RFID at all. So this makes it easier to adapt it to whatever you want, if it's doorway system or some art-related system. For example, one application we saw with another reader, with a commercial reader, which we found really nice, is that they put, for example, the C64 MIDI files on the RFID card, and you could just swipe them over the field, and the computer played a tune that is stored on the card. And for example, if you have 5 cards, because of anti-collision, it was able to make a playlist of all tunes stored in and stuff like this. So it has nice possibilities to play with this, but you don't have to need to have have a running PC around. So it uses only few power, and it basically will survive a long time because no fan, no mechanical parts are involved. The basic idea of this OpenPICC project was to develop in the end an open RFID card emulator, but to be able to... Oh, okay.
We'll first finish with the OpenPCD, and then we go to the card emulation side. Just 1 second, switching the laptops again. Okay, so we now know the capabilities of the hardware. We still don't know how the firmware is actually being written, how it is developed, what kind of development environment we have, and how we actually bring a compiled firmware image onto the device. So the standard, we are using a standard GNU toolchain for ARM7, binutils 2.16, GCC 4.02. Don't ask me why these specific revisions. Some people have made apparently good results with that combination of versions, and we have made we didn't find any bugs and whatever. So those versions prove to be stable. We have some custom makefiles to create the flash images, and basically there's 2 different kinds of flash images that we are talking about, because we have 2 different ways of actually flashing the firmware into the device. One of them is called Samba. It doesn't have any relation with the Samba project of Andrew Tidgell and others. which is for Windows file share emulation. No, this is Samba by Atmel Corporation. And this is basically a built-in mechanism in the Atmel microcontroller that we use, which enables you to... It's a little bit clumsy. You have to first disconnect it, then you set a jumper, then you reconnect it, then you wait for 10 seconds, then you disconnect it again, you get away the jumper, then you connect the device again, and then you can flash over USB. And if you don't do it 10 seconds long enough, then it doesn't work. So this is like the last resort, which we can always use. We use that for initial programming of the device, and you can use it if you brick it otherwise. But because of this clumsy mechanism, we developed what is called DFU, which is a device firmware upgrade. Very little people know about DFU. It is a standard protocol that's specified by the USB Vendor Association and intended for USB device firmware upgrade, exactly for this purpose. Unfortunately, we're not aware of any vendor actually using that protocol. But anyway, that's a standard, so I implemented a standard, and now we have DFU. So once we have used the Samba mechanism to flash the DFU into the flash, we can use device firmware upgrade to do further firmware updates. This is, as Milosch indicated, this is very fast, and you don't actually need to put special buttons or something. If you're interested in DFU, go to the usb.org website, download the specification. It's fully documented. And basically the idea is that you send a special command on the control pipe, and then you reset the device, and then it enumerates with different endpoints, and then you can flash it over that interface, then it resets and it enumerates again with the new firmware. And that whole process, even though it still contains lots of debugging code, only takes like 5 seconds or something. So actually, you can dynamically reprogram the hardware even from your application if you want to do that. I haven't done that yet, but it's possible. So we have the makefile can create basically a dfu.bin file, which is the device firmware upgrade. Oh, somebody corrected the sound. Thank you. You create a dfu.bin image, which is the device firmware upgrade, the bootloader, and you create a firmware.bin image, which is the actual firmware, whatever it does with the RFID reader, and you can actually just concatenate them, and then you get the .samba file, which you can use to flash using Samba if you need to do that in any case. So that's basically the build environment. The OpenPCD firmware is hackable as indicated. We have the DFU for programming. For the actual host side programming, for Samba there is a project called SAM7 DFU. There's a, what is the name of that that Samba upgrade? Anyway, there's for the Atmel Samba flash mechanism. There's already a Linux-based free software tool which you can use to flash it into the device. 1891 flash, exactly. Yeah, that was already there. It's a free program, and the SAM7 DFU is the device firmware upgrade, which is inside the firmware. And then there's a program called DFU Programmer, which was already available on SourceForge, implemented about 90% of what was required on the host side for device firmware upgrade. So DFU Programmer doesn't actually implement DFU according to the standard, but according to some proprietary changes that a specific vendor made. And this had to be changed, so now it's fully standard compliant. As I said, we can always recover. So there's a number of firmware images available currently, as some of them serve actual practical purpose, some of them are only for debugging. So if you check out the subversion tree, or you download the source tarballs of the OpenPCD releases, then you will find the possibility to build multiple firmware images. So you can, the standard firmware for regular production use is called main dump reader. Dump reader because it implements a passive dump reader, one of these where the RFID protocol stack actually runs on the host PC and not inside the device firmware. We also have other images such as main librfid, main analog, main PWM, main reca. I'm going to talk a little bit more about them shortly. The firmware source tree is organized in a couple of directories. Lib just contains some generic C library routines for locking, for bit operations, for stuff like printf and whatnot. there's something called source OS, which is not an operating system. It's just when I wanted to make that directory, I didn't come up with something more intelligent. It's basically the shared code, like the common drivers for hardware that is used in both the OpenPCD and the OpenPICC project. Because as we will learn later on during this presentation, the emulator is from a high-level hardware point of view and from a host software point of view very similar in architecture to the reader. Then there is the source PCD directory where all the device, the OpenPCD, the reader-specific code resides. There's the source PICC directory for the OpenPICC or OpenPICC tag side. There's source DFU, which contains the device firmware upgrade implementation, and some low-level assembly startup code in source start, and finally some scripts. I don't know why the USB forum choose to have, what is it, UTF-16 little endian encoded strings. Actually, this is wrong. So there's some scripts to convert strings into that encoding. So the USB protocol that the firmware talks to the host is using a vendor-specific protocol, so it's not like trying to be a human input device if it isn't one, or trying to be a serial device if it isn't one, but rather it's a vendor-specific protocol. It has 3 endpoints. Unfortunately, we cannot have more endpoints. That's the restriction of the hardware. But we can work around that. So we have a bulk in, bulk out, and an interrupt in endpoint, and all messages, the USB transfers have a common 4-byte header. There's no documentation of that protocol, but there's all the source code on the host side and on the device side, so whoever wants to write something compatible has 2 example implementations. So the main dump reader firmware basically exports 4 primitives on the USB protocol. The primitives are all related to the RC632 ASIC. You can read registers, you can write registers, you can read the FIFO, and you can write the FIFO. That's basically it. And using those primitives, you can implement the full 14443, layer 1 to 4, A and B, and 15693 on the host side. So the device is just a stupid translator between USB and the 632 ASIC. This is the main production firmware as of now, because librfid on the host side has already worked with other RFID readers before, which have a similar architecture. So this is basically designing the firmware to match with existing software design. And that's why the most features are available in this configuration currently. There's firmware images for debugging, such as the main PWM, which you can use to transfer arbitrary pulse width modulated, it's obviously on a 13.56 megahertz carrier. It's an off by 1 error. Even in non-integral numbers. Anyway, so you can create PWM signals, which is basically arbitrary waveforms, arbitrary phase, arbitrary frequency, pulse pause ratio, whatnot. And you can control that using a serial terminal emulator on the UART port, the debug port of the device. So this is easy to test link layer characteristics or to do debugging. If you write some device like a sniffer, if you develop a sniffer or something like that, you can use this PWM to check whether your filters are correct and whatnot. So, but for regular users, it's not really exciting. Then we have a firmware which is called the main RECA firmware. Rec A is the name of a specific packet in the ISO 14443A protocol, and that firmware can be used to repeatedly transmit either rec A or WAP A, which is request A or wake up A, or it can go repeatedly through the anti-collision. The progress, as in did it work, was did the anti-collision finish successfully or whatnot, is again shown on the serial port, and it's also again mainly for demonstration and debugging, but this would be a starting point if you want to write some application. So you loop until the anti-collision finishes, and then you do something else which you might want to do in your application. There's a main MyFair firmware which is almost exactly that, which basically contains code to repeatedly dump one page of a MyFair Classic card inside the reader firmware. There's no host software required at all. Well, you need a Minicom or CU or some terminal program, but anyway, the RFID stack runs in there. This currently only works if the Infineon default key is used, because that's hard-coded in the code. So if you use different keys, you have to recompile. It's, again, for demonstration and debugging. Now, let me first digress one slide on librfid before getting to the main librfid firmware, which is where I suppose most of the future development is going to happen. So the librfid project predates OpenPCD by quite some time. As I said, I originally wrote it for the OpenMRTD project, which is free software for reading biometric passports. And it supported the OmniKey readers, and now also the adding support for the main dump reader firmware was extremely easy because of the existing support for other readers based on the same reader ASIC. The librfid project has a different homepage. It's even though it's used by OpenPCD, it's a separate project. So yeah. Anyway, where is the main librfid firmware? So it basically then the next step after having main dump reader firmware in combination with librfid on the host PC. The next logical step was to port librfid to run inside the firmware environment that we have in the device. So librfid has been sort of, all the POSIX dependencies that it had to run on a Linux-based host system have been removed, and all the external accesses have been encapsulated. And then you can use a cross-compiler to cross-compile librfid for ARM7. And then you can link that library into the device firmware, and that's basically what we call main librfid. And this basically provides you with the full high-level API of librfid that traditionally people only were able to use on the host PC inside the firmware. So you can, if you've written an application that uses the librfid API on the host PC, you can just cross-compile librfid for the ARM7, link it into the OpenPCD firmware, and then you can run your application inside there. And that works very well. I mean, I was surprised how good it actually works. So the main problem in quotes currently is that we have either the totally intelligent device or the too intelligent device or the totally dumb device, because the main librfid currently doesn't offer USB access. So basically you can only run your application fully inside the device, or you can run fully on the host, but you cannot have like the stack in the reader and still accessing it from the host. That's one of the to-do items that are still left open. And if you want to venture into that, feel free. We will do it whenever we find the time. I can't give a precise estimate on it. So I'm already drafting or designing a USB protocol specification for the main librfid firmware to sort of take that further. Another thing that I would be interested in doing is emulate USB CCID, so basically emulate a contact-based chip card reader, because that gives you way more software compatibility, so you can run it, for example, using existing OpenCT CCID drivers, or you can use it with OpenPGP, because with GPG, which implements OpenPGP, you can use GPG, which supports CCID-based, contact-based chip card readers. And if we emulate a USB CCID profile, then that could be used without any software modifications. Also, sometimes people think of other operating systems, which I personally find always strange, but then there are people who use Windows and the like. By the way, librfid and that the whole code base, it has not been written specifically for Linux. It just uses basically libUSB, which is now available on macOS, Solaris, Windows, FreeBSD, and Linux at least. So the host software part should actually be very easy to port to different operating systems. And we would certainly be very happy to merge changes if somebody was doing that. But I personally, and I don't think Milosch either, have an interest to provide Windows port or something like that. Another thing that I would like to look into is emulate the ACG serial protocol on the debug port that the OpenPCD has. That again gives you way more interoperability, because currently there's no software or hardware, no software API nor hardware protocol that sort of abstracts an RFID reader, even in the 13.56 MHz world, from the application. So whenever you write an application, you write specifically for a certain reader. And so software such as RFID, which is RFID IO toolkit, by the way, doesn't have anything to do with an idiot. And RFDump could be used because they support the ACG readers, which have a specific serial protocol, and if we emulate that protocol, then it could also work with the OpenPCD. So it's just a matter of re-implementing that serial protocol. And then another to-do is writing a nice front-end for the RX and TX, sampling the bit banging for SSC that Milosch has been talking about. Stuff like host software to recover the data and to do host-based analysis of the bit stream and stuff like that. And this would really get us way further in enabling people to do crypto analysis on MyFair Classic, for example. And there's lots of other interesting projects, and volunteers are always wanted. Now I'm going to basically end on OpenPCD at that point. Going to talk a little bit about generics on OpenPICC, and then Milosch will again talk about the hardware. And after we're done with that, we will do some demonstration and be available for questions. So OpenPICC is basically the counterpart of OpenPCD, and the terminology, for those who are not that familiar with the ISO standards, is actually taken from ISO 14443, because PCD is the proximity coupling device, which is the reader, and PICC is the proximity integrated circuit card. Yes, there you go. So the idea, and if you look at it from a chronological point, it's also might be interesting to you for you to know that we developed OpenPCD because we had a contract to develop OpenPICC, and in order to develop OpenPICC, we needed a reader that we can fully control, so we had to build one. Always these dependencies. It's not just like apt-get, so. The OpenPICC basically tries to emulate existing RFID cards, and again have something that provides you all the interfaces where you can get to all the signals at any level, where all the hardware schematics are available, where all the device firmware and host software is available under a free software license. And in order to because those two projects are so closely related, in order to keep the development effort as little big as possible, I cannot say small, is that we reuse the same microcontroller, so we can use the same USB stack, the SPI driver, we can use lots of the parts of the firmware, and we can also use stuff like the device firmware upgrade and some host tools and whatnot, so basically all that infrastructure has already been in place. However, there are no ASICs available for the transponder or tag side. It's logical, and therefore an analog front end and demodulator had to be built discrete from scratch, and that's where Milosch is going to take over at this point.
Okay, next try for the microphone. I will show now an introduction into OpenPICC. And sorry.
But can't you read the screen? Come on.
We're hackers. Better. Okay. The basic idea was that there are, in fact, front ends available. They are used for near-field communication, but we haven't found any front end that could emulate all the standards we needed. So there was no use of having such front ends. because we want to have full control. So we want to get rid of proprietary stuff we don't understand, like this RC632, and we didn't want to play the same game for OpenPICC by using another proprietary front end. The most important part was for not choosing such a front end was that it already removes capabilities to do strange stuff with the interface. You have less capabilities, you are restricted in bit rates, you are restricted in binary patterns. For example, what we definitely wanted was capabilities like saying, hey, I'm 1000 tags. So this was also a core design feature we needed, and obviously it's hard for a front end, or it's not meant to be used such a front end, so it doesn't provide such capabilities. So it didn't make no sense to use such front ends, and we had to design it from scratch. So as I indicated, it's basically the very same hardware. The approaches are also very same. Again, this time we didn't take the 13.56 carrier clock from the oscillator, but we instead took it from the field, which required some smoothing and filtering. But basically, it's very same. We have the picture, whatever. We basically have the carrier. The carrier is converted to a digital signal, fed into the timer again. The timer can be configured to whatever frequency we want. So we can have a frequency that is synchronous to the carrier signal. We can shift the phase again, so we again have full power. So all the features you know from OpenPCD for sampling and replaying stuff are initially meant to be implemented from PICC, and we just took them over. And there was one core design decision which was definitely hard for us. The question was, obviously all these protocols are designed to be done in silicon, so they are highly optimized to be done with as few as possible transistors and whatever. So it would make sense to use an FPGA to do the hard work, to get the bit pattern, to remove the real-time constraints. But on the other hand, we thought, okay, we want to support, we want to be open to as many as possible contributors. And I think it's very hard for a person that never did VHDL design to create contributions. So this would restrain people to the existing implementations for existing modulation, demodulation schemes, and only very few people will be able to add such a code for new cards. And I think, in my opinion, this groups won't match the people that are interested in security and software, in evaluation of computer security. Usually are good coders but bad hardware designers, and hardware designers usually not interested in security. So I think this would be like a break for this project. So therefore we decided to go to the hard way and do everything in software. So to be able to do this with as inexpensive as possible CPU, we carefully chose the device. And if you have a look at the schematics, you find that we use very heavily the hardware acceleration features that provides not only the timers, there are several timers used. We, for example, use functions that are used for telephony protocols to act like trigger conditions on data. There are reconfigurable timers that make sure that the timing constraints are managed, so you don't have to do a silly synchronous design, but you can do a really intelligent reader design where you don't have to poll constantly, but you set up stuff correctly, and most of the work is meant to be solved in hardware, so you can do your stuff in software without having to know much about real-time programming. So, for example, for the channel reader to tag to reader, you can pre-compilate all your symbols, just store a buffer, and you say, hey, send it to the reader this and this time. So I think it's very convenient how it currently is. And now you also understand why you have all these debug output features on the OpenPCD device, this U.FL outputs, because you have this U.FL outputs on the OpenPICC. You can create your modulation patterns, see it on one channel on the oscilloscope, and you can see how they result in demodulated patterns on the OpenPCD. So you have the whole chain, and you have full control of every aspect of the protocol, of the analog part, of the digital part, and you can quickly resolve problems. And it proved to be very, very helpful already. This was our first prototype. First time we had fear because the reader field was extremely strong, even if it's not capable of traverse a range of, say, more than 8 centimeters. If you simple task like having an oscilloscope wanting to measure on OpenPICC, it automatically forms some loops. You can't remove them really, and you have the very strong carrier everywhere on your desk. It's in the lamp, it's everywhere. It's everywhere with a strong 13.56 megahertz signal, and you can't see anything. Therefore, for the first prototype, we said we want to play safe. We have one PCB to get a design that is always the same, so we don't have a wire-wound antenna. And we keep it separate from the actual device, from the actual circuit. There is also another topic. There were also two possibilities to solve this topic in software and to solve it in hardware. But as I indicated, we want to make it as simple as possible. So, for example, if you look at modulation, demodulation patterns, they are naturally all aligned on a timeline, and you have a clock or whatever where these are relatively aligned too. But in this particular case, as I indicated, we use the reader field to generate this 13.56 megahertz digital signal, which is derived by our timer signals to our internal clocks. It's used all around the place for our timers, for our counters, and whatever. But the problem is, if you have certain cards, the modulation is 100%. This means automatically that the signal is away, and after a given time, it's there again. But during this time, you naturally don't get any cycles. So it's like the world had stopped for the Open PICC card. For example, the pulse width ratios won't match anymore because each modulation pause will only be 1 or 2 clocks instead of the real amount of clocks, and you had to do dowdy hacks to get meaningful signals out of that. So therefore we decided it's a good idea to use a PLL to lock it to the carrier signal, and to use this to maintain the carrier phase correct while the carrier signal is away during a modulation pause. And this proved also to be very helpful, because then you can instantly dump the data you got over DMA. You just, for example, assign, for example, an underscore to 0, say a age to high level, and you can instantly print it on a console, and you see the bit pattern like you would see on an oscilloscope. This was, by the way, also main design criteria, that the device itself can be set up and operated without special equipment. it is meant to be, if you have an oscilloscope, it's obviously fine, but you don't need one to operate it. And if we have a logic analyzer, it's fine, but you don't need one to operate this. So therefore, we integrated these core features like being able to sample a signal at a high frequency, to be able, for example, to tune the antenna without an oscilloscope. We integrated all these features inside this board, so you, in our opinion, you don't need any special equipment to operate this device. So it's self-contained, basically. Okay, this is how it looks like. It's for the sake of coolness, it's credit card sized. It all again is 4 layers. You see again the 4 turns, and as opposite to OpenPCD, we choose a white as an opposite to the reader. So this is the and you again have a JTAG adapter, but in this case it's really helpful, because to maintain that such tight timing, you definitely want from time to time use assembler to, for example, if you have a high frequency interrupt routine where you want to do some strange stuff, you think you want to do it in assembler. And then a JTAG interface helps greatly. For example, if you're unsure that your code hasn't trashed, for example, internal registers, you can stop it at each time, read out a register, and let it running. So there are possibilities, and if you're interested, we can point you afterwards to places where you can get such JTAG adapters freely. There are open source projects around this, so there is a possibility to get them at reasonable pricing. But you have the same concept, the debug interface. You can do again your printf stuff, and so for higher level stuff, you can easily use it as a self-contained device. Okay, so the basic idea was naturally for reverse engineering. So this means if you, for example, examine the protocol of MIFARE, that at one point you have the opinion, okay, it could work like this, and then you can use this device to instantly test your assumptions. So this is a tool for iteratively reverse engineer protocols, and you find out what's important in a protocol and what not. So the device, because we have this, we can actually demodulate the reader data that we see. You can also use it as a dump sniffer. You can just, the range is not very good, but you just put it between the reader, the reader and your real card, and you can easily get the decoded digital data over DMA. So you can reverse engineer simple cards very quickly, and you can even do a replay attack easily, because you have the same possibility. You have the possibility to send out data which is directly sent to the load resistors, which form the reverse path to the reader, and you can actually take the sample data and replay it. So possibilities like taking the device, using the internal button to record a card which is in a briefcase somewhere or in a bag, whatever, and then use it again to replay it in a door step. So these attacks are already possible with this device. One main cause is also fuzzing attacks. So because we are in full control of even the lowest layers of the protocol, we can introduce all kinds of violations. So you can see me automatically violate different areas and look how the readers react to it. If it breaks, if it stops, and it's a perfect tool for this, in my opinion. Because you can sniff data with this, you can obviously, as long as you know the algorithm which is behind it, you can use it for offline key cracking. And if you do the full emulation, you can replace your lost RFID tags, you can create backups. Okay, what's still missing? So you're getting a rough idea where we are currently at. We are currently working at the anti-collision, which is exactly this nasty part where you have to use very tight code, where we have to comply to very tight timing constraints. And the great thing about this is, as soon as the anti-collision is over, we are set. Basically, you only have to do this is the only place where real time is vital. All other places could be emulated on the PC. So this means that if you have this device, you are able, as soon as you have the anti-collision over, to take over from host side. So you can develop a complex application locally on your host PC. You can locally debug it, and it will supply the necessary data over RF interface and the therefore virtually emulated tag. And because we are full control, we can behave like 2, 3, or 1,000 devices virtually, because we can basically send collisions easily. This, for example, enables to exploit this anti-collision algorithms, and, for example, allows easy denial of service attacks on readers. So you can basically stop it. You don't need a bag with 10,000 of cards, which won't work anyway, but you just use this device and behave like you were an insane amount of tags. And you can do this in a clever way. You can, for example, leave random spaces and whatever. So I think it would be very, very hard, I think in my opinion impossible, to fight against such attacks, because you are in full control, because it's software in the end. And what we want to see in future, I think this is a very hard task, is this reverse engineering of MyFair encryption algorithm to again prove the world that proprietary algorithms that nobody knows how they work are not a good way forward. So I think this could prove an important tool for doing such tasks. And what's currently low priority is ISO 15693 emulation support. It's basically only the bit layer, and the timing constraints are less critical, basically. Okay, so what we want to achieve in future. Currently we have hex dump, so this is not very readable. It works really reliable. If you send thousands of packets, you get basically only a few packets that have errors in it. So it works stable in this aspect. But what we obviously need is some tool that knows the protocol, decodes the bit patterns, knows about protocol state, and provides a nice verbose output like we are all used from TCP dump and other tools. Yeah, and as soon as the basic ISO 14443 and ISO 15693 support is up, it's very simple to add emulated card profiles. Because we have plenty of space there, you can even emulate multiple different cards with the same device. So as soon as they're documented, it's only a matter of hours or days to implement such a protocol based if you have the bit layer set. So say anti-collision and the modulation demodulation. So what we expect is that as soon as we provide this tool, that other people will come and implement all this proprietary RFID protocols, so others can again play with this and check the underlying software layers for problems. So this is the basic intention. And what would be also nice is just to do this copy and paste action with electronic passports. Harald?
Okay. Yeah, this is really a bit blurred. Unfortunately, I don't think. No, this is huge. Anyway, I hope it's readable. There's nothing I can really do about that. Yeah, so I just want to give you a quick walkthrough on how the firmware and the host software environment looks like. So this is now basically the firmware directory of the OpenPCD package that you can either download as a tarball or from Subversion. Basically, here you see I've already built main dump reader and main OpenPICC firmware, but just as an example, I can basically I thought I have it here. Anyway, let me see whether I have the compiler in the. Nee, jetzt erst mal zeigen. Anyway, I'm not recompiling the firmware now, but I can just show you the reprogramming of the firmware to see the speed. Basically, you can use this DFU programmer, OpenPCD DFU dnload /main dump reader bin. So now it's basically reflashing the device. Now it's finished. It's resetting the USB bus, and after that we have ignore the error messages. It's working anyway. So if you look at this, you can actually see there. This is it's only a single device attached to it. So yeah. Anyway. Yeah, I don't need to show you the USB device is there. So now we can. I have the main dump reader firmware in the device, and I can use RFID utils. So there's basically a tool, for example, called librfid tool, which has a help message, and I can, for example, say stay in a scan loop. So it's scanning. It tells me there's no OMI-key reader. Yeah, well, there is another reader, which it doesn't tell you. But anyway, so now I have the reader here, and I can. This is a number of cards, and I can just go here, and then it tells you I found this card with that UID, and then I can move to the next card, and then it's false. Okay. Yeah. But anyway, yeah, here you can see different UIDs of different cards in here. Yeah, this is not a release version. This is a version 3, current development version. It's always a good excuse. Anyway, so this basically, and the librfid tool can do other stuff. So you can basically say, well, I want MyFair Classic, and if you're specifically interested in MyFair, there's also a MyFair tool which can read sectors and whatnot, and so on. Anyway, that was just a quick demonstration, so you can see how this is actually being used and whatnot. I could also show you the source code, but then you can show yourself the source code just by checking the subversion tree. Yeah, so I think now we will be able to take questions, and